Most developers are doing cloud wrong, and the proof is not in their architecture diagrams. It is in their bills, their incident logs, and the quiet dread their teams feel every time a major traffic spike is coming. The cloud was supposed to make everything easier, cheaper, and more reliable. For most teams, it has made things more expensive, more complex, and fragile in ways that are harder to diagnose than anything they dealt with on premises. The reason is not that cloud is bad. The reason is that the mental models most developers bring to cloud are wrong from the start, and nobody corrects them until something expensive breaks. The first thing most developers get wrong is the assumption that moving to cloud is the same as optimizing for cloud. These are completely different things. When most teams migrate to cloud, they take what they had on premises, virtual machines, databases, load balancers, and they recreate the same topology on AWS or Azure or GCP. Same architecture, same assumptions, same operational patterns, just hosted somewhere else. The result is that they pay cloud prices for on-premises thinking. The entire financial model of cloud depends on elasticity. You pay for what you use when you use it. If you are running virtual machines, provisioned for peak load around the clock at 15% average utilization, you are not using cloud. You are renting expensive servers from someone else and calling it cloud transformation. Go through your account right now and pull a utilization report on every compute resource you are running. Look at average CPU and memory utilization over the past 30 days. If you have instances consistently running below 30% utilization, they are candidates for right-sizing, for conversion to auto-scaling groups that shrink during low traffic periods, or for replacement with serverless or container-based workloads that scale to zero when demand disappears. The waste in most cloud accounts is not hidden. It is sitting in the utilization metrics that nobody is reviewing regularly because reviewing them was never made anyone's explicit responsibility. The second thing most developers get wrong is IAM. Identity and access management is the most powerful security control available in any cloud environment, and it is almost universally misconfigured in ways that range from mildly reckless to catastrophically dangerous. The pattern is always the same. A developer needs to get something working quickly. Scoping permissions precisely takes time and requires understanding the exact API calls the service needs to make. Giving administrator access or attaching a wildcard policy takes 30 seconds, and it works immediately. The ticket to scope it down properly gets created and never prioritized. Lambda function, every EC2 instance role, every developer account in the organization, and you end up with a permission structure where a single compromised credential can do almost anything to almost everything. The principle of least privilege is not a security recommendation. It is a hard requirement for any production cloud environment. Every identity gets exactly the permissions it needs to perform its function and nothing more. Implementing this correctly requires going through every policy in your account and for every permission asking what specific action by what specific service at what specific resource requires this permission right now. If you cannot answer that question precisely, the permission should not exist. On AWS, use IAM Access Analyzer, which shows you which permissions have been granted but never exercised in the past 90 days. Those unused permissions are attack surface you are maintaining for zero. Operational benefit. Remove them this week. Set a recurring calendar reminder to do the same audit every quarter because permissions accumulate over time and drift toward excess without active management. The third thing most developers get wrong is designing exclusively for the happy path. Every architecture looks reasonable when all the dependencies are healthy. All the network calls return on time, and the deployment exactly as planned. Cloud infrastructure is reliable enough that these conditions hold most of the time, which is precisely what makes designing only for them so dangerous. The failure modes that cause real production incidents are almost never the obvious catastrophic ones where a whole availability zone goes dark and your monitoring screams. They are the subtle ones. The database connection pool that exhausts silently are an unexpected load pattern. The third-party API that starts returning errors intermittently and causes your retry logic to create a thundering herd that makes everything worse. The cache that fills up and starts evicting entries in a pattern that sends cascading requests directly to a database that was not provisioned to handle them. Every service you write needs to assume that every dependency it calls will fail at some point and needs to handle that failure in a way that degrades gracefully rather than propagating the failure upstream. This means timeouts on every network call without exception. A network call without a timeout can hang indefinitely and tie up a thread or connection indefinitely and eventually exhaust the resource pool of the calling service. It means circuit breakers that ECT when a downstream dependency is failing and stop sending requests to it instead of continuing to hammer a service that is already struggling. It means bulkheads that isolate failure so that a problem in one part of IR system cannot consume all the resources of another part. It means testing these failure scenarios deliberately rather than discovering them in production. Pick one critical dependency in your most important service. Take it offline in a staging environment and watch what happens to the services that call it. What you observe in that test is what your users will experience in production when that dependency fails unexpectedly. The fourth thing most developers get wrong is treating cloud cost as a finance problem rather than an engineering problem. The bill arrives once a month and gets reviewed by whoever manages the budget, and the conversation that follows is always reactive. It is already too late. The waste has been accumulating for 30 days, and the architectural decisions that caused it are made months ago. Cloud cost is an engineering problem that requires engineering solutions applied continuously, not a financial problem that gets addressed after the damage is done. Every resource in your cloud environment should be tagged with, at minimum, the team that owns it, the service it belongs to, and the environment it runs in. Without tags, you cannot attribute cost to the decisions that created it, and you cannot make intelligent optimization decisions because you do not know what is driving the spend. Set up billing alerts that notify the relevant team immediately when spending crosses defined thresholds so that anomalies are caught in hours, not weeks. Use your cloud provider's cost anomaly detection tools, which can identify unusual spending patterns automatically. On AWS, this is Cost Explorer with anomaly detection enabled. On Azure, it is cost management with budget alerts. On GCP, it is billing budgets with alerting thresholds. The tooling is already there on every major platform. Using it is a decision, not a capability gap. Review your reserved capacity and savings plan coverage quarterly. On-demand pricing is the most expensive way to run predictable baseline workloads. If you have services that run continuously at a reasonably predictable size, converting that capacity to reserve D instances or a savings plan on AWS can cut the cost of that compute by 40 to 60% with no architectural change required. The math on this is straightforward, and the savings are immediate. Most teams leave this on the table because nobody owns the decision and the procurement process feels more complex than it actually is. The fifth thing most developers get wrong is data transfer costs. This is the single most common source of bill shock in cloud environments, and it is almost entirely invisible during development and testing because test environments run at low traffic volumes where transfer costs are negligible. In production at scale, they are not negligible. Every major cloud provider charges for data leaving their network. Outbound transfer to the internet, transfer between availability zones within the same region, transfer between regions, transfer between cloud services that cross a billing boundary. These charges accumulate silently and they scale linearly with your traffic. Map your data flows explicitly. Draw every path data takes through your system and identify which of those paths cross billing boundaries. Data moving between services in the same availability zone is typically free or very low cost. Data moving between availability zones costs more. Data moving between regions costs significantly more. Data moving out to the internet costs the most. Once you have mapped the flows, you can make targeted decisions. Place services that exchange large volumes of data in the same availability zone. Use a content delivery network to serve static assets from edge locations instead of transferring them from your origin servers on every request. Compress data before transmission. Implement aggressive caching at the appropriate layers so that the same data is not fetched and transferred repeatedly for every user session. None of these changes require significant architectural rework. They require knowing where your money is going and making deliberate choices about it. The sixth thing most developers get wrong is manual infrastructure management. If anyone on your team can make changes to production infrastructure by clicking through a cloud console, your infrastructure is not reproducible, not auditable, and not recoverable in a predictable time frame when something goes wrong. Console changes leave no record of who made the change, what the state was before the change, or why the change was made. When something breaks after a manual change, which it will, the debugging process begins with archaeology. When you need to recreate an environment for disaster recovery or for spinning up a new region or for matching production and staging, you're doing it from memory and from tribal knowledge held by whoever made the original decisions. Every resource in your cloud environment should be defined as code. Terraform, AWS CloudFormation, AWS CDK, Pulumi, Bicep for Azure. The specific tool matters less than the discipline of using one consistently. That infrastructure code lives in version control alongside your application code. Changes go through a pull request with review and approval before being applied. The Cloud Console is used for observation and debugging, never for making changes to resources that matter. Treat a manual console change to a production resource exactly the way you would treat a manual edit pushed directly to production application code without review. It is a process failure that needs to be corrected, and the conditions that made it feel necessary need to be addressed. The seventh thing most developers get wrong is confusing uptime monitoring with observability. A service that responds to a health check endpoint with a 200 status code is up from a monitoring perspective. It can simultaneously be returning errors on 40% of real US. Our requests, exhibiting latency that makes it functionally unusable and silently corrupting data in edge cases that no health check will ever surface. Uptime monitoring tells you whether the process is running. It tells you almost nothing about whether the application is working correctly for the humans using it. Real observability requires three things working together, and none of them can substitute for the others. Metrics give you aggregate pictures of system behavior over time. Request rates, error rates, latency at the 50th, 95th, and 99th percentiles, not just averages, because averages hide the tail latency that your worst affected users experience. Logs give you the detailed record of what happened for specific requests with enough context to diagnose a problem without needing to reproduce it. Distributed traces show you how a single request traveled through every service and why. Our system, how long each step took, and where failures occurred when a request did not complete successfully. Without all three, you're operating with significant blind spots, and you are finding out that something is wrong when users report it, rather than when your systems detect it. Instrument your services with structured logging from the beginning of the project, not after the first incident. Use a log format that machines can parse efficiently because at production scale, you will be querying millions of log entries and you need tooling to do that. Implement distributed tracing using OpenTelemetry, which is the open standard supported across every major cloud provider and most major application frameworks. Define your service level objectives before you deploy. An SLO is a precise statement of what good performance looks like for your users, expressed in measurable terms. 9.9% of requests complete in under 200 milliseconds. Error rate stays below 0.1% over any rolling 7-day window. When you have defined what good looks like, you can build alerts that fire when you are trending toward bad, rather than alerts that fire after you have already failed your users. The eighth thing most developers get wrong is treating security as a phase that comes after the application is working. Security decisions made during initial development cost almost nothing to implement correctly. Security problems discovered in production after a breach or after an audit cost orders of magnitude, more to remediate and carry reputational and regulatory consequences that dwarf the engineering cost. Unencrypted databases because encryption was not checked during provisioning. Public storage. Buckets created for a temporary test that were never locked back down. Overly permissive security groups opened for a debugging session and never closed. Secrets committed to source code or stored in environment variables because a proper secrets management solution had not been set up yet. Every one of these is a decision made under time pressure that becomes a liability that compounds indefinitely. Encrypt every data store at rest. It is a configuration option during provisioning on every major cloud provider, and the performance impact in modern managed database services is negligible. Use your cloud provider's secrets management service for every credential your application uses. AWS Secrets Manager, Azure Key Vault, GCP Secret Manager. Rotate secrets automatically using the rotation policies these services provide. Enable audit logging on your cloud. Account so that every API call is recorded in a tamper-resistant log. Review your security group and network access control rules quarterly and remove any rule that cannot be justified by a specific current operational requirement. The developers and teams that use cloud well are not the ones with the most resources or the largest platforms. They are the ones who treat every one of these disciplines as non-negotiable, who build review cycles around them, who make explicit ownership assignments so that cost, security, observability, and infrastructure quality are someone's actual job rather than everyone's vague responsibility. The cloud rewards this discipline directly and visibly in the bill, in the incident frequency, and in the confidence the team has when something does go wrong that they will find it fast and fix it cleanly. Pick the mistake on this list that most closely matches what your team is doing right now. Fix it completely before moving to the next one. That is how the gap closes.